So I'll talk about asynchronous data dissemination. We call it ADD in short, and this is a joint work with Jolun and my advisor Lindgren. We are all from UIUC, and this will appear at CCS 21 this one. So let's get started. So this is the outline of my talk. I'll give a brief overview of our uh, overview, and then I'll talk about system model. Then I'll define what ADD is, and briefly explain how we use ADD to improve reliable broadcast. I'll also describe what reliable broadcast is, and I'll summarize my talk. Hopefully, I'll be able to do this all of this in 15 minutes. So, overview: we introduce something we call asynchronous data dissemination, and we realize that we can use this primitive. So, this is a primitive that we introduce to improve communication cost of many other primitives in asynchronous systems like reliable broadcast, asynchronous verifiable secret sharing, ADKG. So, and in particular, we can shave off a factor of log n from almost all of the things in the same setup. For example, if we look at reliable broadcast, we can shave off a factor of log n from here and we get a communication cost, which is kn squared. So k is the security parameter. And throughout the talk, I'll mostly focus on communication cost of these primitives. So these has many applications, like we can do state machine replications on blockchains, like host of BFT. We can also do asynchronous multi-party computation like Honeybadger MPC, HBABS, ACSS, lots of other things. So this is the system model that we work in. So we consider an asynchronous systems where message delays between honest node could be arbitrarily long, but the messages will eventually get delivered. And we consider the setup assumptions. We mostly work in common random string, which means everybody has access to a hash or like uniform random string, or sometimes in public infrastructure. For our ADD, we do not assume any setup. It's information theoretic, but for reliable broadcast, we assume common random string or hash functions. So what is ADD? So ADD is this very simple primitive that we have a network of nodes where some nodes are honest, which are the blue and the black ones are the honest. Some nodes are bad, red ones. And a subset of honest nodes starts with a common message M. And the remaining honest nodes starts with bottom, like they don't have any message. And they know that they don't have any message. And we want to run a protocol which is parameterized by n and t. N is the total number of nodes in the network, and t is the number of malicious nodes. So that at the end of the protocol, all honest nodes have the message m, output the message m, and we don't care about adversarial nodes. So this is the ADD primitive, and we want to solve this. So at this moment, it might not be obvious why this primitive is useful or how we get to this initial condition where some honest nodes have the message, others do not have. So we'll get to all of these in a while. So we focus on T, the number of corruptions, which is less than 1/3. But we can do this, solve this ADD problem for T less than half, but we don't have much applications for T less than half. Most of the applications are for T less than 1/3. So let's first look at some naive approaches with n equals to 4 and t equals to 1. So two nodes starts with the message. So we require that at least t plus 1 honest node starts with the message. So t plus 1 will be 2. So two honest node will start with the message. And one primitive we can have is all honest nodes who start with the message sends the message to everybody so that everybody can output. But it has communication cost of n square m, which is which is too high for us. We don't want this. Another approach is, so this is a push model we have seen, like nodes that start with the message push the message across to other nodes. We can also consider a pull model where nodes that do not start with the message can request other nodes to get message. But here an adversarial node can ask the message from all the honest nodes and can increase the communication cost to n square m. M is the message, m within straight brackets is the size of the message. So these do not work or work even we have high communication costs. So we want something which is more efficient. And our protocol will be very simple, but it uses something called error correcting codes, and which provides, so we particularly work with Reed-Solomon codes. Error correcting codes essentially provides us two interface. So first interface is encoding that says you can treat the message as k plus 1 symbols. Symbols means binary string, and we can encode the message and extend it to M symbols such that during the decoding, we do not need all the M symbols. We can work with T symbols, and then of which some could be erroneous, and we can recover the original message, K plus 1 symbol. So this is a very standard primitive. We use it as our building block. So I'll now describe our protocol for how we solve ADD. This is very simple. So what we do, all the honest node that starts with the message first applies this encoding procedure to get four. So here n is 4. So they get, after the encoding, they get 4 small message blocks. So which we denote M1 to M4. So the first node will get this block, second node will get this block, third node will have nothing, fourth can do whatever it wants. So this is the encoding phase. And once they encode, first two nodes will have these vectors of messages. And what they will do, they will send the ith message to the ith node. For example, node 1 sends M2 to node 2, M3 to node 3, M4 to node 4. Similarly, node 2 will also do the same. So each node sends ith message to the ith node. So what will happen at the end of this dispersal phase, honest nodes will, the nodes that starts with the original message will set mi star to be the message that they have. Like mi star 1 will be m1 because they can locally compute m1. The interesting case is node 3. What node 3 does, it waits till it receives t plus 1 identical m3s. And once it receives t plus 1 identical m3s, it sets m3 star to be m3 prime. And the idea is there are at most t bad nodes, and the node 3 is receiving t plus 1 identical messages. That means one of the messages from honest node. That's why the message M3 star that the node 3 sets is a right encoded block. So this is the dispersal phase. And at the end of the dispersal phase, we start reconstruction phase where where every node just gossips, multicasts the mi star they have. So this is reconstruction phase. So small mi's are small messages, capital M is the large message. And at the end of the reconstruction phase, node 1 and node 2 will output the original message because they already have it. Node 3 will wait to receive 2t plus 1 mi stars, and then it will run the decoding procedure to recover M. So this is the overall protocol. This is very simple, only 2 steps, dispersal and reconstruction. Now let's look at the communication cost. So in the first phase, dispersal phase, so the size of the encoded message is proportional to the size of the original message. So the communication cost is everybody sends a small message, and the size of small message is size of capital M by N. So the communication cost of the dispersal phase is N times M plus N squared. And also communication cost of the reconstruction phase will also be the same. So at the end of this protocol, we get ADD, which has communication cost of N times M plus N squared. This is much better than N square M, NM square, which we had earlier from the naive protocols. So far we talked about ADD. Now I want to briefly talk how we use this to improve the reliable broadcast primitive. Before I talk about that, I'll briefly define what reliable broadcast is. So reliable broadcast is this primitive. Now we start with a single node that has the message M, and we want to run a protocol RBC so that at the end of the protocol, every node outputs the same message. So this is different from ADD. Here we have only one dealer, and rest of the nodes are recipients. So one naive approach one can think is that why not the dealer simply sends a message to everybody and everybody outputs it. This won't work because the dealer could be malicious, and it might send different message to different nodes, and everybody will output different message. We don't want that. We want to emulate a broadcast primitive where the dealer can say only one thing in the broadcast channel and everybody will output the same thing. So more formally, RBC primitive needs to define 3 things, which is called agreement, that every honest node outputs the same message. It also says it requires validity. It says whenever the dealer is honest, every honest node should output the dealer's message. And we need totality, which says whenever a single honest node outputs, every honest node should output. So I'm going fast with these primitives. It might take some time to internalize these properties, but we'll move ahead and we'll talk about one of the famous, most classic, and one of the very efficient protocol of achieving RBC, which is Bracha's RBC from 80s. So this protocol has very simple interfaces. The first thing is the proposal phase. Here, the dealer is the first node. What the dealer does, it sends the message in a proposed message to everybody. At the end of this phase, all the nodes upon receiving the proposed message just multicast a echo message to others. Like they just forward the message to others, and everybody does this. So this is called the echo phase. And after the echo phase, once a honest node receives 2t plus 1 echo for the same message, it sends a ready message to everybody. Or the node can send a ready message if it receives t plus 1 ready messages. And upon receiving 2t plus 1 ready message, everybody outputs the message. So this is the classic Bracha primitive. It can have 4 communication routes, and it's very simple. Downside of this protocol is the communication cost of doing this is high. So in the first step, we have proposal, which is n times m, which is okay. But in the echo and the ready phase, we have communication cost, which is n square m. We don't want that. Cashin and Tesaro in 2005 improves on Bracha's original construction to assumes hash functions and provides a construction that has a communication cost n times m plus kappa n square log n. So it has a factor of log n because it uses Merkle trees. So we use ADD to improve upon this communication cost. But before I do so, I want to state a theorem from Bracha's RBC. So I'll state it very informally, but it'll give the message. It says, if we run Bracha's reliable broadcast, we can guarantee that whenever an honest node outputs a message M in Bracha's RBC protocol, then at least T plus one honest node sent echo message. So this we can prove using quorum intersection. And this is very crucial because we use this to establish the initial condition of ADD. Recall in ADD, we have a situation where T plus one honest node starts with the message, other do not start with the message, and we want all honest node to deliver the message. So we use this RBC theorem to make sure that we get the initial condition of ADD. Then the new RBC protocol is very straightforward. This is our same as Bracha. The leader proposes the message. Now everybody, instead of echoing the message, we echo on hash of the message. And then we do the same, like ready round is also same. We just send ready on hash. And what happens, once honest node receive enough ready message, they start the ADD protocol on message M. And at this point, we can argue that we establish the initial condition of ADD so that once we run the ADD protocol, everybody will output the same message M. And we get a reliable broadcast primitive. So if we look at the communication cost here, so we have n times m in the proposal phase, which is same as Bracha. In the echo and the ready state phase, we have kappa n square because everybody only gossips hash, not the original message. And then in the ADD phase, we have communication cost of ADD. So if we combine all of this, so what we get is communication cost of our new reliable broadcast primitive is n times m plus k n square, kappa n square plus cost of ADD, which is n times m plus kappa n square. So this is an improvement. We essentially remove the log n factor from the communication cost of RBC. So this is our protocol. And in summary, what we do, we can use the same structure to improve many other asynchronous primitives. And the idea is same. So we pick a asynchronous primitive and we formulate the problem as a dissemination of a large message, typically the linear size message. And then we establish initial condition of ADD using the Bracha primitive. And then we run ADD. So this is the general structure in all our applications. And there are some other applications where we have to do something more non-trivial to establish the initial condition of ADD, but it's all boils down to how do you establish the initial condition of ADD and then run ADD. So again, in summary, we propose and design ADD, and then we show how we can use ADD to improve reliable broadcasts, ABSS, ACSS, and many other things. So this is kind of concrete communication cost. We can shave off a factor of log n from most of the things. Yeah. And that's it.
Okay, thank you very much. We